To date, we've covered a number of fairly complex topics as we've learned about phylogenies and phylogenetic reconstruction. My goal is to try and give you an overview, a simplification, maybe give you a taste of how some of these things are implemented with software and using the Mega program. But I understand that it is quite technical and a little bit complex and difficult for many students to understand. This is an upper division course, so there's a little bit about that. I have students tell me that the best thing about this class is there is no textbook, right? Because they don't have to buy a $200, $300 textbook. But the worst thing about this class sometimes is that there is no textbook. I understand the papers can be a little technical and difficult to get through. My goal is not to have you memorize them or read them in a ton of depth, but to use them, go review them. Maybe if you're interested in certain parts, go into them a little bit more detail and use them as background and preparation for what we get from these discussions. Now, depending on the class, you may have been assigned this Irasati and Zardoya paper. It's, again, kind of middle range, good and bad. It's a little technical, but it does a good job of covering it and isn't too inaccessible. So if you have read it, if you're in the class where you've read it, great. You'll recognize much of what we're talking about. If not, that's fine. You can look it up. Just search for the thing if you want to review it, but it's not necessary. We're going to, again, try and summarize these complex topics here in our PowerPoint discussion. Okay, so we're going to be looking at testing alternative hypotheses. Now, so far what we have done is, as we've looked particularly at the maximum likelihood and Bayesian tests, we've talked about our hypotheses being the phylogenies themselves. And that's certainly true, but you realize that in this discipline of biology, there are other hypotheses we can test, and we use the hypotheses of the trees as a roadmap or a background for testing other hypotheses, and then those trees become a tool for doing that. Now, anytime you're testing alternative hypotheses, you need some sort of a statistical test to either accept or reject the alternative hypothesis. To say, hey, is this hypothesis A, is it significantly different than hypothesis B? And then we run some sort of a statistical test to determine whether they really are significantly different. Now, to do any sort of a statistical test, you need a distribution, or what's called a null distribution, right? So you might have something like this where we've got phylogenies that are scored based on a maximum likelihood or parsimony score, and you get lots of them that have bad scores. And as you get farther and farther and farther up, you find the very best tree, maybe a small number of them, that have very, very high scores, right? And so basically what we're doing is we're looking at an alternative hypothesis and saying, is it significantly different from the very best tree? But to do that, we need to know something about the distribution, right? So if the distribution is very, 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 very flat, then maybe our alternative hypothesis is not significantly different from the others. Now, there are a number of tests that can do this, and we're not going to get into all the details of how they work or even memorize the names. I'm just going to give you one example. A Shimodera-Hasegawa test, or SH test, basically uses a distribution, and this distribution, if we're looking at phylogenies, the distribution can be generated by randomly generating a bunch of phylogenies and seeing what their score is, and coming up with a distribution of scores for phylogenies. And you probably will get something like this with your very best tree being here on the far end. And then we can test alternative hypotheses. So let's say an old researcher published a different hypothesis, maybe based on molecular data, or maybe based on morphological data. And so we could test whether or not our data really support the very best tree is significantly different than the older hypothesis. And if it's a very, very strong test, you'll get a very high p-value, sorry, very low p-value, right? And you'll be able to reject the idea of this new hypothesis being similar to the very best one overall. Now, there's a Kashino-Hasegawa test, which is slightly different. Again, we're not going to get in the nuts and bolts of it. And there's one other called So the other test is the approximately unbiased test. Again, these are fairly complex statistical tests that for the purpose of this class we're not going to get into. You probably won't even get into them in your stats class unless you're a graduate student and majoring in stats or minoring in stats in a graduate program. So anyway, don't worry about it, but just understand that they work like any statistical test, and we have to have a distribution. and then perform some sort of a statistical comparison between one thing and another, or a population of things and another. And then we either accept or reject based on that statistic. Okay, so to generate our distribution, we use a bootstrap procedure. We test these alternate hypotheses. And so we might do something very simply like this. Here are two competing hypotheses. One is that the marsupial mammals are most closely related to the placentals, and the other is that the marsupials are most closely related to the monotremes. And so we could gather a large data set, and we would come up with an answer to this. But if there are other people or other data sets that are supporting an alternative hypothesis, even though our data says, well, this one's the very best one. By the way, it's A is widely supported now. This one's the very best one. Say, okay, but how much better is this set of relationships, this hypothesis, than this one? And if we have a statistical test, and we can strongly refute this hypothesis when compared to this one, then that becomes a very good argument for our set of relationships. And so the likelihood ratio test compares the likelihood of one tree versus another, runs it through the statistical test, and comes out with a score. And then that score gives you a value based on that distribution. Okay? So we can use this likelihood ratio test to test different phylogenies, but it is widely available. And the likelihood ratio test revolves around the Kishino-Hasegawa, the approximately unbiased, or the Shimodera-Hasegawa. Those are all kind of preambles to the likelihood ratio test. And the likelihood ratio test is the final comparison between those two values. So as I said, we could test different hypotheses, but it's widely applicable, and there are 3 other applications, and other ones too, but these are the big ones. 3 other applications of the likelihood ratio test that you need to know. The ones we have not talked about yet, but we'll get into them in a lot more detail. So we can use a likelihood ratio test to determine whether a molecular clock is appropriate for our data. Now, a molecular clock is a way that allows us to estimate divergence times. So it's a really powerful tool if it's available, but we need to even see if we can do it. And so we can use this test to determine, can I use a molecular clock, either accept or reject that hypothesis of a clock-like model of evolution. And if it is a clock-like model, then suddenly we can do all sorts of things inferring divergence time for different groups. And we'll come back and we'll explain more about exactly how that works and look at that in some data. Okay, number 3, we've already mentioned this one, and so we won't do any more of it after we mention it here. But the likelihood ratio test was how we were determining whether or not we're going to accept a simple model or a more complex model. We compare them, and we do this in sometimes an iterative approach or in multiple ways, so we compare, so we don't get locked into one single pathway of comparing all of the different models of evolution. And then we run a test and say, is, based on the likelihood ratio test, is the more complex model that much better? And if it is, then we use it, and that becomes a way to select our model of evolution. So the likelihood ratio test does that. And it's, again, we calculate 2 different ones. We look at degrees of freedom. This is a little bit more in detail. I don't care that you spend time memorizing this, but we get a value, right? A p-value. It has to be more or less than that. And if it is, then we accept or reject. In this case, since our value is 4.53, it needed to be at least 9.49 to be better. The GRT does not significantly better fit than the simpler model, and so we choose the simpler model in this case. Okay, but just give you kind of an idea of what's going on. Now, these are implemented in software packages, and so are rather fast to do in most cases. And there are many different alternatives in software packages that allow us to do this. Okay. The final one that we're going to learn about is a very interesting one, and we will come back to it just like for the molecular clock. We'll come back to it at a later date and do it in more detail. But this is looking for signs of selection. If you've had an undergraduate evolution course, this is going to be familiar to you, and we'll spend more time on it in this class and learn it in more detail than you did in the undergraduate one, or I guess maybe for some of you it's a lower in the just the introductory evolution class. And so we can look for signs of selection across protein coding genes. So this is only applicable to protein coding genes. And we can do it for a single site, we could do it for a single gene, or in this analysis, which is a just recently submitted analysis of the Hymenoptera, the ants, bees, and wasps, particularly looking at the eusocial, right, the truly social bees that have hives and queens and division of labor. And what they found was across many, many different genes, there was a relaxation of purifying selection. Now, if that doesn't mean anything to you right now, don't worry about it. For some of you, you'll be able to remember it from the 3301 class. But if not, that's okay. We'll come back to it later. But basically, think of it, we can look if there are different types of natural selection acting on genes. And we do that using this test. We say, here is a null hypothesis. Do we accept or reject the idea that there is a significant variation from that null hypothesis? And if there is, in this case, we have a relaxation of purifying selection, which is in this kind of bluish color. And you can see there are some weak relaxation of it across, but in here, the truly social bees, there's this very strong relaxation. And I thought this was a very interesting paper because they use that across many different genes as a sign that this eusociality has a direct impact on the evolution of the genes in these organisms. And so it's that likelihood ratio test that gives us the comparison so that we can determine the difference between them.